Just sort of a little aside, kind of about where we're, or like where we are and where we're going at this point. Um, I think, I think this will be probably the last day we're going to do Agda. I know, like typically I would put out a new module on Wednesdays, and I haven't put out. So the reason is there's a few more things I wanted to go over. Like there's going to be a module with on Agda stuff, but it's going to be due after spring break. I haven't decided exactly what we're going to do next week. Wednesday, actually, I'm going to be attending like a virtual conference, so we're not going to have class on Wednesday. But I want to go over a few things today that I would that are cool, and I'd like you to be able to use on the module. So that's what we'll do. And I'll let you know what we're going to do next week. But I just wanted to kind of give you a heads up on what. Also, you may or may not be thinking about the fact that like we haven't had a quiz in a while. We're supposed to have like a quiz for module 4 that we haven't had. And I'm not. It was hard for me to come up with like what would be a good quiz for module 4. I just have to think a little more about what we're going to do with those. But I'll let you know that too. Just to let you know that I'm thinking about it. All right, so let me show you something cool. So we did a few. Well, we didn't actually finish that, did we? Oh, I think we didn't actually finish that. Cool. Well, that's a good segue into what I want to do anyway. So we were just talking about how to prove different things about functional programs, right? So as an example, we had this this length function implemented in the usual way that we would write it, just directly by recursion. But then we also have a version of length that is implemented using full-art, and we just wanted to prove that they're the same. Oh right, we were running into the problem that, I remember now, yeah. That Agda was not producing this, and so it was maybe a little hard for us to see what we had to prove. However, I want to show you something that is going to make this. So I still don't know how to, like, actually it is possible doing like a bunch of, you can type in a whole bunch of commands to get to do that, but to work around the fact that we can't hit certain keys. But we don't need to do that. So instead, we could actually think about, okay, well, length f of x cons x's, we kind of think about what does that reduce to, and we could kind of do a bunch of steps ourselves. The problem is it's hard to do that in our head. Right. But there's a way that we can actually write down a proof by a bunch of steps like that, so that Agda is helping us keep track of like where we are and what we have to do. Okay. So that's what I want to do. So I'm going to actually, no, no. So in Agda, you can have import statements wherever you want. But it has to be, you have to put them all at the top, right? So I'm going to say, if we already have lists defined, you may have that. You can just need, oh, did I already import that? I guess I already imported that. Oh, of course I did, because oh no, we defined the call yourself. Okay, right, that's right. binary versions of list and natural numbers. It's the same as what we defined, but just this relation binary propositional equality that gives us like the equal sign and things like the fact that it's transitive and symmetric and Kong and those things we talked about before. Also, REPL. And then we're also going to say, yeah, okay. So this thing is really cool, and I'll show you what that gives us in just a second. Actually, maybe I want to find the documentation for it. Most of this we can ignore. I want to find. Oh, never mind. All right, forget it. I thought we could find some helpful documentation, but no. I'm just gonna tell you. I'll remember as best as I can. All right. So here's the thing. We are trying to prove an equality here, right? So it tells us the thing we have to prove is that length x cons x's equals length f of x cons x's, right? So if I just asked you to prove that kind of on paper, right, one way you might think about doing it is by, if I could do like a sequence of steps where like this is equal to this, is equal to this, is equal to this, and finally I get that it's equal to this, right? If I can make a sequence of equality steps like that, then because equality is transitive, right, the first thing is equal to the last thing. And so actually, there's this equality reasoning thing gives us the ability to write proofs like that in Agda. So what I'm going to do is I'm going to say, here's the thing I have to prove. So we get some operators defined in here. For example, there's this little symbol which is defined by this, which just says like, that's how we mark that we're done. Yeah. Okay? And this thing, it's actually, this operator actually has three arguments, right? The first argument is this. The second argument is the thing in between the brackets, and the third argument is what comes after it. Okay? Basically what this allows us to do is to create a proof that this thing equals this thing according to the reason in here. Okay? So far we haven't really made any progress because now we still have to prove the exact same thing. But the point is we can chain this. So we can actually have like multiple steps. And we just have to give the reason for each step. Okay, so we can actually construct it. And of course, how does that work? I mean, it's using transitivity under the hood. So actually the definition of this thing is really not that complicated. It's basically just trans, more or less. But it gives us kind of some fancy notation, right? And so we're really making use here of the fact that Agda allows kind of arbitrary, operators that have arbitrary numbers of arguments that could be like in between different symbols and stuff, right? So this, like these symbols together are like a 3-argument function that happens to use this funny syntax where like you have an argument and then some symbol and then another argument and another symbol and then an argument. How it parses that is pretty complicated, and it's, I mean, there's like a whole paper that someone published in a academic paper about how to do this kind of parsing, because it's not obvious how to do it. But they got it to work, and it works really well. So it's telling me that yes, indeed, you have to prove that log is less. So I look at this and I say, okay, well look, length of x cons x's. Well, I know that the way length is defined, it's going to be like 1 plus the length of x's, right? So what I'm going to do is I'm going to make another line. Right, so I can have a series of steps, and in between each step I just have to put the reason. So now if I look at this, it's telling me, okay, now here you have to prove that length of x's equals, well, okay, and now, see, it did actually reduce somewhat in a way that we probably didn't want it to do, but, oh well. You know what, okay, here's what I'm going to do. I'm actually going to define, let's see. Let's define length ourselves. I think it's going to be a little bit easier to see what's going on. Okay. So I hid the length from the standard library, we just find it ourselves. So now, right. So actually, now it's actually reducing it for us, and we can see that really these are the same just by definition, right? They look different, but just because of the definition of length, this is just how length is defined, right? Length of x cons x is equal to this, so Agda can just see that these are equal without really needing any proof. It's just like, well, if you just compute them both, reduce them both, you get the same thing. So the proof here, I can just put REFL, right? Because to show that something is equal to itself, I can put REFL. It turns out there's also, that's a common enough thing that there's a special notation for that. If you want a step that's just REFL, you can actually put the library provides this special symbol, which basically means, we don't have to give a reason. It's just, they're literally the same. Agda can tell that these are the same, so I don't have to give a reason there. So you can just leave it empty. But I could also, it's the same as saying, okay? How about this? Well, let's think about length f of x cons x's. Well, I mean, length f is defined as fold r, so I could actually just, if I replace this, so this should be x cons x's. And I think these should just be the same by definition. Whoops, Control W. These should just be the same by definition, so I don't really have to give a reason for that. That's just the definition of length f. Okay, so we're making progress on both sides, right? And eventually we hope that we can fill in all the reasons, right? But at any given point we have at least one step that has a hole, and we're like, okay, there's some missing argument here. Well, fold R, we know what fold R does when this is a cons. So this is going to be function applied to x and polar of that function on x's. Which, I mean, I don't know, we could write this out if we want. We could just say, look, what that function does is it's going to ignore x and just return 1 plus whatever. So it's going to be 1 plus that. So we still know that one. This one should also be just by definition also. What about this step? This maybe the most interesting step. So on the left I have 1 plus length x's, or down here it's reduced it to successor of length x's. And over here I have successor of fold r blah blah blah. And both sides have a successor, right? And so if I could show that this part is equal to this part, I could use the Kong thing to say, well, if these inside parts are the same, then Kong tells me that I can apply suck to both sides of the equals and get that the whole thing is the same. So I guess I could say Kong suck. And it says, yeah, you can apply suck to both sides as long as you can prove that length x's is equal to fold r blah blah, then you get what we want. And why is this? Are these equal, or how can we show that those are equal?
Have the empty ones, both of them are going to return 0.
That's true. That's true, but that's, I mean, that would only, I want to show this is true for any list x's. Yeah, and like, well, yeah. One thing to notice, right, here I have fold r of lambda underscore L, blah, blah. That's actually the definition of length f. Can you see that? Which kind of makes sense. Like I started, like the f was here. Length f is defined as this fold r, and the fold r kind of reduced one step. But kind of behaving, yeah, and then it reduced to, you know, this is the same as length f. So really, to prove this, I can use my induction hypothesis, right? That's what I'm proving. I'm proving that for list x's, length x's equals length f x's, which is this fold r. So I should just put this to the length. So I don't know if this is the best example. I mean, the interesting thing is you notice that all the steps were just reflexivity except this step. And so actually we didn't really need to use this kind of step-by-step reasoning notation. We could have just written this, Kong, suck, blah, blah, blah. We could have just written that here. And that would be accepted. It was just hard for us to see that because Agda wasn't fully reducing, both sides of it, so we couldn't quite tell, what steps it would just do automatically and what steps we would have to actually. And so using this notation kind of helped us go a little bit more step by step. Right? We could do the steps ourselves, but then have Agda check that yes, that is a valid step, right? We're just like, I think this would equal this, right? And it's like, yes, that's right. Like, okay, well, and then this, I can make one more step to this, right? And it's like, yes. And then you're like, okay, now I see, I just have to prove this. All right, well, let's do another example where, have an example in mind where we really do kind of need this. Like, it's going to have several steps that are non-trivial, and we would need to, if we kind of did it manually, we'd have to use trans several times. Like, we'd use transitivity a bunch. But using, writing it like this, we can kind of keep track of the steps. What I want to do is, let's see, I'm going to define a type of binary trees. A tree is either or it's a node. I'm going to define two functions on trees. I'm going to define a size function that takes, for any type A, it's going to take a tree A and return a gnat. Okay, and how's this going to work? Well, so I'll pattern match in the tree. If it's empty, and by size I just mean like basically the number of nodes, right? The number of A's it has in it. So the size of empty is 0, of course. And, oops, I forgot. That's a list, that's not a tree. Let's give it another subtree. Call this left and right. So what do you think I should put here? What's the size of it? If I have a tree that's a node XLR, it should be the size. Yeah, that's right. And I'm going to actually I'm going to do it this way. I'm going to put the plus on the middle. Again, just because I know what I want to prove, and it's going to be slightly easier to do it that way. Otherwise, I'd have to make use of commutativity addition and stuff. But this way, all right. And then I'm going to make a function called flatten. That takes a tree of A's and returns a list of A's. Basically, it just does a traversal of the tree and takes all the A's in it and just gives you a giant list. Okay, so flatten. Let's pattern match in the tree. If it's empty tree, we just give the empty list. And if it's node XLR, I want to say flatten my left subtree first, turn the left subtree into a list, and then we'll have just the root value by itself in the middle, and then we're going to flatten all the things on the right. Does that make sense? So what I want to prove is, I didn't even know what to call it. So for any t, which is a tree A, the size of t is equal to the length of flattening t. In other words, to get the size, one way I could use this size function, or I could flatten it, turn it into a list, and then take the length of that. Again, this is not earth-shattering, but it's going to be a good example to show this. All right. So let's pattern match on t. So for an empty tree, I have to prove that 0 equals 0. Great. Done. Base case is always easy. Not always. Right, and why was that? Well, because, if T is an empty tree, then the definition of size says that's 0, and then the length of, the definition of flattened says that's the empty list, and the definition of length on the empty list is 0. So Agda was able to just reduce all those, and said, oh, in this case, they're both 0, so. Alright, this case is obviously more interesting. And so we're going to use this same notation. So the thing I want to prove is that size L plus 1 plus size R, or well, really the thing I want to prove is that size of node XLR is equal to oh, and I should say, maybe make these special brackets are just like backslash, less than backslash bracket. Length function of XLR.
I'm guessing that's written to parse those specific.
What was that?
I'm guessing that's written. The parser's written to parse those specific forms of brackets.
No.
This? No? Because I remember you saying something about how it was, anything that was open, or like symbols that were on both sides or something.
No, yeah, no, it doesn't. So like, it literally, this is defined in a library. It's not built into the language at all, right? The library just says, oh, I'm defining, it would be something like, saying, I'm defining this operator named this, which has some type, blah, 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 and it's defined as this. And yeah, just the Agda parser can, you can arbitrate things like this. Can parse it. So no, it doesn't care that like one is open and one is closed. You could put whatever symbols you want there, and it would still be able to parse it. But that's part of why it requires spaces to write everything, because if it, like the spaces help it know like what actually is its own thing. But well, I guess we don't require spaces like around parentheses frequently. And you're not allowed to use parentheses in a symbol that you define, right? Parentheses are special, but most other things you can use parentheses. Okay. So in this case, I need to show that the size of this thing is equal to the length of flattening that thing, right? Because this is a case where T is actually a node XLR. And, for some reason, and of course we're going to expand this into a bunch of steps. So let's just start from the top, and we'll see, there we go. So we'll look at this and say, okay, size of node XLR. Well look, I can see what the definition of that is. That's size L plus 1 plus size of R. So let's go ahead and put that in. So this is actually going to be size L plus 1 plus size R. And, okay, we need to fill in a reason, but we think this should just be by definition, right? So we shouldn't actually need to give a reason. We can just do that. And we load it, and it says, yes, that's good, right? If it didn't work, we would get an error at this point. Like if let's say, what if I put 2 here or something? Let's just to see what happens. And if I now try to load it, it says, nope, error. In fact, this error is actually pretty good. It's like, yeah, 2 is not equal to 1. I was checking that, this thing matched the thing I expected to see, which was, now of course it's a little obscured here because it's like, this isn't reduced, right? But, my point is, it really is checking something here for us, right? The fact that it loads means that yes, we were right, that this by definition is equal to this. And we just haven't yet filled in the rest of the reasons why this is equal to this. So So right, the fact that, so I will say, like, it's certainly possible to put something here, well, it's checking for us, it knows that, like, this is the right thing to prove, given what we're trying to do here. But if I set this up with a, like an incorrect, like if I try to prove something that's false, a false equality, like it would be okay with this so far. It's like, yeah, I don't, like, the fact that we're missing a proof here, it's like, okay, this is what you're trying to show. It doesn't know if it's true or not. So we could try forever and like not ever find a proof. But if we finally do fill in all the things, then that's when we know for sure that it's true. All right, well, I don't know. I don't see any obvious way we could make progress with this. Like, I'm looking at this and I don't see any obvious way I could simplify that. Right? Because I don't know what L and R are. And, but we could simplify this on the other side. So let's work from the other end. Well, flatten of node XLR is defined to be this, right? So so it should be length of that. That should be also by definition. Okay, good. Any thoughts on this? How we can simplify? Can we simplify this at all, or can we say anything about this? I'm trying to find the length of the concatenation of, flat L plus a single X plus flat I. Yeah,
Could you not apply length to flat to what's the depth?
yeah. So you want to say something like, it should be like length of, flatten L. And then like, what do I do with those if I apply length to all of those? Add them all, yeah. Good. So yes, that should be true. However, Agda doesn't know that. And so, this is actually the point where we say, aha, this is a fact about length, how length interacts with plus plus, that I believe to be true, right? That if you take the length of something plus plus something, it's the length of the first plus the length of the second. So that's a lemma that we're going to have to prove. We'll have to prove that. And we should prove it as a separate step, okay? So, I'll call it length plus plus. So I want to say, for any type A, if I have a list, and for any x's, which is a list of okay, I need x's and y's, then length of x's plus y's equals length x's plus y's. Okay, x's, y's. Oh, what? It's not plus plus. Plus. Well, let's probably pattern match on x's, I'm guessing. I don't know yet if we're going to have to pattern match on y's or not. Let's just try x's, because plus plus certainly needs to pattern match on the first one. Okay, so in this case, if x's is empty, then it tells us, yeah, now your goal is to prove that length y is equals length y. That makes sense, because if x's is the empty list, like empty list plus plus y is just y's. And over here, length of the empty list is 0, so 0 plus something is just, so that is just going to be in this case, any ideas what I should do here? I'm trying to prove that successor of length x's plus plus y is successor of length x's plus plus y.
You can do the Kong thing.
You can do the Kong thing, right? Yeah. So I can say Kong same thing we're trying to prove just on, actually these x's and y's are like smaller. Well, the x's is getting smaller, right? Because this x is actually like the original x's tail, right? And if you don't like the fact that Agda kind of by default, when you pattern match on something, it kind of gives the subpart the same name as the original thing, which can be a little confusing when you're looking up here and it says x's and y's, and you're like, well, that's exactly the same thing I started with. Like, wouldn't this be infinite recursion? But it's actually a different x's. You can always rename this one if you want. You know, call it x's prime or something, or call it t for tail or something like that. Why don't we do it just for fun? Right, so now, look, it's saying length of t plus y is equal to length t plus length y. But the point is that this function works for, you know, for any list x's. And so, I should be able to say length plus plus. Well, and this is one of those cases where probably the nice thing I can do is I can just say, yeah, use length plus plus, and I don't know, I'm going to do Control C, Control A for auto. Just like, yeah, figure out what arguments need to go in there. Yeah, t and y's. You know, I might even be able to put underscores there, because Agda can probably figure out that it has to be t and y's just based on the type of the proof we're trying to make. Right, so, no, okay, it doesn't like that. It's like, yeah, I can't quite figure out what you're doing here. What if I just give it t? And then I can figure out the other one. Okay, cool. So now we can use that lemma, and I can say, so here is actually a slightly tricky thing. When I write flatten L plus plus list of x plus plus flatten R, does that mean flatten L plus plus x plus plus flatten R, or does it mean flatten L plus plus x plus plus flatten R? I'm actually not sure which it is. It depends on the associativity of the plus plus operation. But we can figure it out, I guess.
Would it be difficult to prove that that's the same?
No, I mean, we might have to. I'm not
Commutative
sure.
addition.
What was that?
Like commutative addition.
Yeah. No. So plus plus, this plus plus operation on lists, it's not commutative. You can't, like, switching the order doesn't change it. It changes it, but it is associative, right? So we can, yeah, it doesn't matter which order we put this in. I'm gonna just like, I'm just gonna add some parentheses and just like have it check whether those are the same. So actually no, it's like no, those are different. So it must be the other way. Okay, now it's happening. So, okay, we know which way that goes. So now, I'm going to use that, so this, according to our lemma, our length plus plus lemma, right, this should be length of flatten L plus the length of that thing, right? Okay, that's good. So hopefully, okay, but this isn't, I can't just do this. Right, because the reason those two things are equal is not just that they're defined to be the same thing, it's because of the lemma that we proved. So we're going to have to actually fill in a reason there. So the reason is, right, why are these two things equal? They're equal because length plus plus, well, and again, I can just say, hey, the reason is length plus plus, and then I'll do auto and be like, figure out what things need to go in there to make this work. So, oh, it didn't find it. Okay. What if I just put underscore in it? Doesn't like that. Well, okay. Length plus plus, so it's that this doesn't work, but it takes the two lists, right? The two lists that are involved. So the first list that is involved is flats and L. And what? Oh, haha. Okay. we proved? We proved that the length of x's plus y's is equal to length x's plus length y's. What do we need here? We need that the length of something plus the length of something else is equal to the length of something plus something. You see how that's backwards from what we proved? So we need to use the fact that equality is symmetric. So I really need to say sim. So sim, when you apply to equality, just like flips it around. So now it's saying, okay, now we have to prove, now it's the same way as what we did. So now we should, I wonder if we can now do this. Yes. So now, the reason auto didn't work before was that it wasn't true. Or it wasn't true by that reason. So yeah, it's because of our length plus lemma, and then it filled in these things. And in fact, we might even be able to say, keep saying it. Might even be able to actually put underscores here. Nope, wouldn't like that. Okay, so again, I can, if I fill in the first one, then it's okay picking out the second one. All right. I don't know if we're gonna be able to finish, but we're gonna do our best. So, one thing I could say, I could use that lemma again, but actually, like in this case, if you do a single x plus something, that's just like plus can see that that's defined as like x cons that thing. So I could delete it. So this is the same as x cons. Alright, and then length of a cons is defined as 1 plus the length of that. Yeah, okay. And if we had used our lemma again, we would have gotten like length of the singleton list x plus the length of flatten r, and length of single list x would be 1. So we would end up in the same place. All right. We're actually pretty close because, so look at this. If you stare at these two, how are those different? Right? They look mostly the same except that, and actually let's make sure that plus, this could be, let's make sure where the parentheses go here. Because if they go the opposite way, then we'll have to. They don't. Haha. All right. That's exciting. Okay. So one problem is the parentheses are the other way, and so someone was talking about, so like plus, for example, is associative. So actually, this is equal to this. Right? Those are equal, but not by definition. Like, it's a lemma that we have to prove. We can prove it ourselves, or it's also proved in the standard library. I don't remember the name of it off the top of my head. It's probably called like plus a soap or something like that. Oh, it's probably like in some other, it's like data.nat.properties or something. I don't know. Yeah, there we go. That's what it's called. So we use the associativity of plus, which is already proved for us in the standard library. So the Agda standard library, in addition to having lots of standard things that you would expect that would be like in the Haskell standard library, it also has proofs of lots of properties about those things. So it's way bigger than the Haskell standard library, because it's like all that stuff plus proofs of it. We're almost done actually. So now, right, these really match up. Size L matches up to length flatten L, and why are those the same? That's one of our induction hypotheses. Right? We can just recursively call this theorem, get that. And the 1 is the same, and then the size R, so we can use Cong2. Right, to say, plus, yeah. Now, oh well, okay, that goal is not very helpful, but I want to prove, this is the proof that size L equals length flatten L, and that is because of theorem L. And then this is a proof that 1 plus size R equals 1 plus length flatten R. And that's true because of Kong suck. And then now I just have to prove that size R is length flatten R, and that's again our induction hypothesis. I just say theorem R. Look at that. Finish the proof. Just in time. Silas?
What is the plus on Sean?
Oh, that's just the name. So it's like just like in Haskell, if you want to give plus as an argument to some function by itself, you put it in parentheses. Like that's kind of how you do that in Agda. Like the name of plus by itself is just like underscore plus underscore. It's kind of showing where the arguments are. Yeah.
So you're just saying those two things.
I'm passing. Yeah.
Yeah,
The first
plus.
argument to Cong2 is the function plus. Yeah. Because that's the thing that it's like you're going to apply plus to two things and show that each side is